This 2D plot shows a classic binary classification problem. We have two distinct groups of data, blue and orange, and our goal is to use labeled training data to draw a decision boundary that perfectly separates them. If the data points are linearly separable, a simple straight line works. But as we move into 3 dimensions, that line expands into a plane. And in even higher dimensions, it becomes a multidimensional hyperplane carving through the data. Calculating the exact position and shape of that dividing boundary across complex dimensions is the primary objective of a neural network. Structurally, a network is divided into an input layer, an output layer, and one or more hidden layers in between. Each node within these layers is a basic processing unit called a neuron or a perceptron. To understand how this entire structure learns to draw complex boundaries, we have to isolate a single neuron and decode its mathematical workflow. First, incoming signals are multiplied by assigned weights. Next, the neuron calculates the sum of these weighted inputs and adds a bias term. Finally, this sum is pushed through a nonlinear activation function, producing the final output signal. Through these calculations, the neuron acts as a pattern detector. If the equation yields a high output, the neuron fires, successfully recognizing a specific pattern from the preceding layer. Everything leading up to the activation function, multiplying weights and adding a bias, is a strictly linear operation. If you stack multiple linear layers on top of each other, the math simply collapses into itself, and the final output remains a flat, straight line. To map highly complex data, we need nonlinearity. The activation function bends boundaries so they wrap around intricate data clusters and normalizes values to prevent them from growing too large. Without this nonlinear transformation, a multi-layered neural network is computationally useless for complex tasks, performing no better than a single linear layer. This graph maps common nonlinear shapes. Sigmoid compresses inputs between 0 and 1. Tan stretches from negative to positive 1. Finally, ReLU allows positive values to pass, while aggressively clipping negative values to 0. Different layers require different functions based on their goals. For a binary classification output layer, we need a clean 0 or 1. So we use the sigmoid function. For multi-class problems, we use a generalization called softmax. Selecting the correct mathematical shape for the activation function dictates whether the network can accurately answer the specific question being asked. If you need to compute the 7th power of a number, writing out the full equation from scratch is difficult. But you can reach the exact same result by cascading simpler functions, using squares and cubes to build up to the higher order calculation. Hidden layers use this exact same cascading effect. Early layers might only identify basic edges or straight lines. By feeding those outputs into the next layer, the network eventually combines them to draw highly complex boundaries. The total number of these hidden layers determines the depth of the neural network. As a rule of thumb, deeper networks possess the mathematical capacity to learn much more complex functions. While shallow networks handle basic separation tasks, stacking layers is what grants the architecture its capacity for deep learning. To summarize the architecture, every neuron multiplies inputs by weights, adds a bias, and applies an activation function. ReLU is typically the default choice for hidden layers, while sigmoid and softmax are reserved for shaping the final output predictions. The entire process of complex classification relies on billions of these simple, micro-mathematical decisions executing in perfect sequence.